Yeah, I submitted it where it was part of last night, but if you didn't finish it, I'll also give you credit. Show me Monday. Yeah. 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 All right, let's continue with graphing. Okay, I think we got through page 37. But just to kind of recap here. Okay, we did finish page 37, right? Yeah. Did we get through? Okay, let's just do a little bit recap here. So we know that with these heart shape or limousin graphs, they have this, there's something that is different than the previous circles. We have this indentation here. If the coefficient and the constant are the same value, it's going to kind of create, it's going to hit the pole or the origin once, and that's going to cause it to kind of have that heart shape about it. If the constant is less than the coefficient, then what's going to happen is that the graph is going to go into itself and it's going to create an inner loop. And if the graph has a constant that is more than the coefficient, then it's going to kind of go in a little bit, but not as much as the cardioids. So it's going to fall in a little bit, but it's never going to hit that pole. So we call this a dimpled limousin. So using your calculator and also using your graphing, see if we can decide what's going to happen with the next set of graphs. So this is page 38. Okay, what do you think is going to be different? If you had to guess, what do you think is going to be different about this graph, 2 plus 2 sine theta? Yeah, heart shape, but now it's going to be what? Symmetrical. Yeah, about the y-axis. Yeah. So same thing here. This is going to be a limousin with an inner loop. And here, this is going to be a dimpled limousin, but it's just going to be symmetric about the y-axis. So we just start off by picking out some easy values, enough for you to kind of have an idea how the graph's going to look. But you can also use your calculator as well. Oh, I do want to show you, if you wanted to find out a value in terms of R and theta, you can do second trace value. But right now, you may be, if you do that, you're getting an X and Y value out of it. So what we can do to get an R and theta to show up instead, if we do second zoom format, you can do polar graph coordinates instead of rectangular graph coordinates. So if you do that, then it'll give you a R and theta in decimal form. So if you do second trace value, and let's say this graph, I wanted to figure out where pi over 3 was. Now it'll give you R and theta in decimal form. So that could be helpful as well. So second trace to get to the value, and then second zoom to, if you want to look at your graph for rectangular polar coordinates versus rectangular coordinates. So all these graphs are symmetrical about the y-axis. Okay, see you. Sometimes to make the graphing a little bit easier, especially if you're trying to find order pairs that are easy to graph, you want to take advantage of the fact that you're dealing with a sine graph. So with a sine graph, typically something that's in that pi over 6 family is a little bit nicer because anything in a sine of pi over 6 will produce something like 1/2, and 1/2 is easier to graph than like √3/2. And then cosine is the other way around, right? Cosine, if you want to pick nice, easy gradient measures, you want to pick something in that pi over 3 family. Okay, it's just, you don't have to, but it's just nice to play with easier values, especially if all you need is to have some idea as to where the graph is going. You don't have to know every single point. So both 7 pi over 6 and 11 pi over 6 will produce a sine theta of -1/2, and that -1/2 times 2 is -1, so that's going to end up giving the 0, and that's going to, these are going to be where that the loop is going to close off right at the pole. And again, if we can sketch half the graph with order pairs, then we can trace the other half just by using symmetry. So that's, you can also use that to your advantage as well. All right, let's look at the bottom of page 38, example 4. All right, so we see something a little different here. It's not just a single angle measure or radian theta value. Now it's going to be 3 theta or something that is inside that theta. And this is going to create these petal-shaped graphs. So one thing I want to point out here is look at what's inside this cosine. You got an odd number here. So an odd number, okay, will indicate the exact number of petals. So here, that n is 3, so n theta, we're going to have 3 petals here. And then the coefficient is going to tell us the petal length or the petal diameter. Okay, so let's see how this graph plays out when we start sketching it. Okay, so again, I'll start at 0. So 0 in for theta. 3 times 0 is 0. Cosine of 0 is 1. 1 times 3 is 3. Okay, start off with pi over 6. Now, this is pi over 6 here, but it's going to get transformed into something else because of that 3 there. So cosine of 3 pi over 6, same thing as cosine of pi over 2. And cosine of pi over 2 is what? 0. So there is a polar 0 here. I'm going to block off polar 0 here. So you see how there's going to be 0 here. Now this is going to tell us that pi over 6 is going to come in at it's going to come in at the angle that you would expect at pi over 6. So the graph is going to come in like this. Okay, next up, I'll choose pi over 3. It says it's pi over 3 here, but that 3 is going to transform it, right? 3 times pi over 3 is pi. Cosine of pi is -1. -1 times 3 is -3. So that means at this pi over 3 line, sorry, it's going to be going across on this side to -3. So 1, 2, 3. So it's going to begin that second petal before it even finishes the first one. Okay, next up, let's try pi over 2. Pi over 2 will cause this to turn into 3 pi over 2. What's cosine of 3 pi over 2? 0, right? So 3 times 0 is 0. So it's going to close in. Symmetrical, yeah. But I'm going to just pick off some more values here. 2 pi over 3. Yeah, so 3 times 2 pi over 3 is 2 pi. Cosine of 2 pi is 1. 1 times 3 is 3. So that means at this 2 pi over 3 line, the graph's going to go to 3. Okay. 5 pi over 6. That's 15 pi over 6. Same thing as 5 pi over 2. If we don't recognize 5 pi over 2, then we know it can subtract 4 pi over 2 to understand that it's really pi over 2. And so cosine pi over 2 is 0. Now at pi, cosine of 3 pi is same thing as cosine of pi. Cosine of pi is -1. -1 times 3 is -3. So at pi, it's going to go in the opposite direction. So that's going to allow for the graph to close off. Okay, so we call this a rose curve with 3 petals. Notice that it completes its full cycle in that interval from 0 to pi. 3 polar zeros allows the graph to close off the petals 3 different times. And because it's a cosine graph, we're going to have symmetry about the x-axis. I didn't want us to have to graph something like sine of 5 theta or sine of 7 theta, but we can kind of pick out some important properties, right? What do you know about 2 sine of 5 theta? We know that 5 theta tells us, 5 petals. The 2 tells us length. Every petal has a length of 2. Symmetry about the y-axis, And here, r equals 4 sine 7 theta. 7 petals. Each petal length is 4, and still symmetry about the y-axis. And again, they're all completing their cycle within 0 to pi. Okay, next page. Is everybody okay? Right, so example 5. Now, if my theta has an even number, then that's going to change things significantly. We can still figure out the number of petals, but now if it's an even number, then it's going to be double that number. So here, 3 cosine of 2 theta indicates my petal length is still 3, but if it's in that n theta form, we have double the number of petals. So 2 theta would indicate we have 4 petals. So let me walk through the order pairs here. Okay, so if I plug 0 in, cosine of 0 is 1, 1 times 3 is 3, so we start here. Plug in pi over 4. Cosine of 2 pi over 4 is pi over 2. So cosine of pi over 2 is 0. So it's going to go back here to the hole. At pi over 2, cosine of pi over 2 times 2 is pi. Cosine of pi is -1. -1 times 3 is -3. So we're going to go all the way down here to that third quadrant there. Right? 3 pi over 4 is 0. So back here. And then at pi is going to be cosine of 2 pi, which is 1. 1 times 3 is 3. And notice that when we reach pi, we are not at the same location as what we started. Okay. And so that's why it's going to take twice as long to complete its cycle. And because it takes twice as long, it's creating more petals that way. We don't have to worry about that. Okay. Yeah. The constant will only be with the limacons. Yeah. The rose curves will not have a constant. Or if it does, they will provide that graph for you. You don't have to worry about doing anything with sketching. Okay, so we expect 4 petals. We complete our cycle in the longer time period because just to pi, it's not like the odds where it ends up in the same place and closes off. It ends up in a different location, so it takes a little bit longer for it to complete its full cycle before it gets to that starting point. And then we can expect x-axis symmetry. Okay, what about for here? Even if we didn't look at the graph here, we can tell how many petals. 8 petals, petal length of 2, symmetry about the y-axis. 6 is an even number, 12 petals, petal length is 4, symmetry about the x-axis. That's true. I think for cosine, you may be able to have multiple symmetries for the evens, but I believe for the odds, it's just going to be either. Yeah. Okay. But yeah, you're right. I think yeah, even does have multiple symmetries. Okay, so we're done with the intro to graphing. I would still like to be ahead with the notes just because I want to buy us additional time for the graph for the area. The area of between polar graphs just takes a little bit longer to get used to. So let's go ahead and start Monday's notes. So page 40. Leave your answer unsimplified. That's fine. Yeah, that's fine. All right. Okay, so we've briefly talked about this. So just a bit of review from yesterday. XY is for a rectangular Cartesian coordinate system. R theta is for polar coordinate system. R is a directed distance from the origin to a point P, and theta is a directed angle. Okay. We talked about before how in polar form, there are multiple ways to identify the same point. In fact, we have infinite number of ways to identify the same point because we have infinite numbers of coterminal angles. So to get from polar to rectangular, we just have to involve sine and theta. We know that cosine theta is x over r. We know sine of theta is y over r. And if we rearrange that, we can get x and y in terms of r and theta. So as long as I have r and theta, I can use those to help get to the rectangular form. And then if I'm sitting at x and y in rectangular form, I can use Pythagorean theorem to get to r, and I can use inverse tangent to get to theta. All right, so number 1, it says convert the following from polar form to rectangular form. So we want to get our equation in terms of x and y. So r cosine theta, replace that with what? X. So x equals -4. That's just a vertical line. All right, 4r cosine theta equals r squared. We're just trying to replace anything that we can to be in terms of x and y. So we can replace something here and replace something here. Okay. R cosine theta gets replaced with r squared is bring everything over to one side here. We recognize this as if we complete the square, we can get it into a circle form here. Okay, b over 2 squared over 2 squared, 4. Factor x squared minus 4x plus 4 becomes x minus 2 squared. The y is just by itself. I can make it y minus 0 squared. So what I have is a circle with a radius of 2 and a center at 2, 0. Okay, next up, number 3, if I cross multiply, I can get that cosine and sine to be in the numerator. Linear equation from here. Okay, so now let's talk about derivatives here. Slope of a curve in polar form. A curve in polar form is given by r equals f of theta. We know theta is the independent variable. R is dependent variable. We can think of r as f of theta. Then its rectangular coordinates are given by x equals r cosine theta. Think of r as f of theta, and y is f of theta sine theta. Okay. The derivative of dy dx is defined the same way as the derivative of a parametric equation. It's just y prime of theta divided by x prime of theta. But x and y have multiple parts to it. So if I want to find x prime and y prime, I need to go through what? Product rule. Yeah. So f prime g plus f g prime, or f prime sine plus f cosine theta. And here, f of theta cosine theta, f prime of theta cosine plus f of theta The derivative of cosine is negative sign, so that's where that negative comes from. Okay, page 41. Okay, the following is an example of a common problem. Theta at theta equals 0. Okay, so we know that if we're trying to convert from polar into slope, we know it's going to be dy over dx ultimately. And we can, or sorry, dy over d theta over dx over d theta. So we know ultimately it's going to be y prime, and we know the theta value, so y prime is 0 divided by x prime 0. Okay, so we'll just break them down separately, evaluate them separately, and then at the end we just divide those values with each other. Okay, so we know that y is equal to r sine theta. Why don't we just get everything in terms of theta, and then we can just find the derivative with less variables. So we know r y equals r sine theta. We know r is 1 plus 2 sine theta. So I'm just going to go ahead and see if I can get my equation just in terms of theta here. Okay. I can do product rule here, or I can expand this out. Okay, sine becomes cosine. Here, I'm just going to rather just do chain rule instead. So outside derivative times inside derivative. So 2 sine theta. Same thing as that, right? You write as 4 sine theta times cosine theta. Okay, I'm going to get all the way down to y prime of 0, and then we can focus our attention on x prime. Okay, so this is nice. Sine of 0 is just going to 0 out. Cosine of 0 is 1. Okay, I'm going to turn my attention to x. X is r cosine theta. I'm going to replace r so I can just get everything in terms of theta and then just worry about how to find the derivative from there. You can distribute through and then do product rule, or do product rule here. So it's up to you. Let me see. I'm going to just go ahead and just do product rule here. Okay, this is going to wipe out. Okay, so x prime 0 is what? Just what? 2. Okay, we got started with this. So no homework this weekend unless you didn't finish page 34 and 35. Otherwise, I'll check that on Monday. But if we got a head start on that, that means hopefully we can get into polar area earlier than Tuesday. Okay, all right, come get your phones. Hey. Okay. Okay, I'll mark it down.
So I have not today, but yesterday.
All right.
Is next period.
Okay.
So can I just say, make sure I thank you. Yeah,